And we don't have a lot of class periods left. So we've got one more week, then we have fall break, then we come back, and then we'll get ready for our final. So we're not going to have any other exams before our final exam. You should already have the practice final. And if not, I can get you a copy of it. But I gave that out about a week ago. But if you need a copy of it, I can get you that copy. I think all of us in here are going to stay for the final. I know my other class, a lot of them are leaving early. If you're going to leave early and not come back to take your final on time, just let me know. And we can find a time to work together and get your final complete. Okay, so we're going to go ahead now and look at question 3 from 4-2. And what we're looking at here on question 3, and I should have wrote it a little bit differently. You want to bring that negative down. So on question 3, rewrite it as this. Okay, when I made it up, I should have been more careful. Put that negative down with it for question 3. And now when you graph it, okay, when we graph an exponential, what do we know about that 5? Well, 5 is going to be what? 5 is greater than that 1, isn't it? So what would my picture look like? It would look like that. Now, what about ours? Ours is going to be where? Below. Are we shifting it up or down any? Are we moving it any at all? No. So I still have my horizontal here at y equals 0. And instead of it being up here, we've got our first point down here at 0, negative 1. And then we need another point, at least one more. You could do 2, but at least one more. So what's our number in front? Negative 5. So that's going to go down 5 and over 1. So 1, 2, 3, 4, 5 over 1. There it is. Connect them together. And your graph should look similar to that. Okay, but make sure you put that negative, instead of it being in the exponent, it should be down below. So make sure it's down below. That way your graph looks correctly.
So always going to have a negative sign immediately?
Yeah. Make sure you put it down below. When I rewrote it, I should have put it below instead of at the exponent. So make sure when you rewrite it on question 3 from your homework, put that negative down below with it instead of as a power. So that way it'll come out to the graph that I want, so the graph will look like this. And why is it going to be down below? Because this is what? Negative. Now, why is it looking in this general shape? Because 5 is bigger than what? 5 is bigger than 1. So that's what your picture is going to look like. And I didn't realize it until I got to the other class that negative was here. You want to make sure that negative is rewritten down below in front of the 5. That way it works out and looks correct. Okay. Another one that we asked about was question number 6. Okay, so we're now going to look at question number 6. 4 to the negative x equals 1 over 16. Different ways of handling this question. The first thing I would probably do, and you can do it all in one step, or you can do it in 2 steps. I'm going to do it in 2 steps. First thing I'm going to do is I'm going to rewrite that 1 over 16 as 16 to the negative first power. Right? Because that's the same. Your negative exponent rule says you can rewrite that. And what do we know about 4? Do I need to move that back a bit? Yeah, I can move that back a bit if I need to. Does that help out a little bit? Yeah. Okay. Yep. Always just let me know and I can do that. So not a big deal at all. So what do we know about 4? 4 raised to what power now makes it 16? 4 raised to the second power. So now when I rewrite it, I've got 4 to the negative x equals 4 to the negative second power. Because the negative there, and we know that 4 squared is 16. Are the bases the same? Yes. Once we know the bases are the same, then the exponents must be the same. So then negative x equals negative 2. Divide by your negative 1. And now we know that x must be what? Must be 2. Is everyone okay with how I did that? Next, we're going to look at question number 8. And question number 8, we're going to have to rearrange again these fractions. And I want you to see how I can rearrange them to make them work. Okay. Right now, as they are, they don't work. Why not? Well, does the 16 go with the 3? No. But 9 goes with 3, right? Because 3 squared is what? 9. And what do we know about the 4? The 4 goes with the 16 there. So first thing I'm going to do is I'm going to rewrite them. So one of these fractions gets flipped over. It does not matter which one, but one of these is going to get flipped over. So I'll just flip the second fraction over. Now, when I flip it over, what is that going to do? That's going to put a negative in front of that, right? And what do I do with this negative here? Distribute it through, and then we're going to see how to finish it out. So distribute that negative through. And you could have done the other side. It doesn't matter. But one of them will get flipped over, and the other one can stay the same. Is everyone all right with that so far? Right? Negative has to be distributed through. Now, what do we know? Okay. Now, when I work with this, what do we know about the fraction? 16/9 is going to equal 4/3 raised to what power? Can someone tell me? What number is going to go here? Okay, look at each one. 4 squared is what? 16. 3 squared is 9, so that's going to make that squared. Is everyone all right with that so far? Now, when I rewrite it, what do we still have to do? Okay, we got another step to rewrite here. So when I go to rewrite this, I now have 16 over 9 to the x plus 1 power. But that's not, well, let me write it correctly here. Okay, we rewrite that 16 over 9 as what? Let me rewrite it so it looks correct. 4/3. Now, it's squared, so we have to put the 2 there, times x plus 1 equals 4/3 times, or to the power, minus x plus 1. Right, so that's what that's going to look like. You always take the larger one, make it into the smaller one. Now, how can we finish it from here? Well, to finish it from here, what can we now do? Are the bases the same now? Yes, the bases are the same. So if the bases are the same, then what do we know about these exponents? The exponents must also be the same, right? Let me find another piece of paper here. So we can set them equal. There it is. And we can solve it. So what's our equation now look like? Okay, everything's the same. The bases are the same. They match up. So the exponents must match up. So now we know we have 2 times x plus 1 equals a negative x plus 1. And we're going to distribute the 2 through. So that's 2x plus 2 equals a minus x plus 1. And move things around. So I'm going to add x. And move the 2 over. So that gives me then 3x equals negative 1. Divide by our 3. And so our final answer is going to be x equals now negative 1/3. Is everyone okay with how I work that out?
Can I ask you to do the number 5 also?
Sure, sure. Yep, we can look at 5 as well. Okay, so question 5, it's actually an easier question because this one, what are we doing on 5 here? Okay, 5, When I look at this, do I have to flip any fractions over? No, I don't have any fractions, right? What do we know about the 6 and the 36? Well, the smaller number is 6, and 6 raised to what power gives you that 36? 2. Okay, so now we can rewrite this as 6 to the 2x power equals 6. Now, if there's no number here, that's an automatic exponent of a 1. Okay, so that's going to be an automatic exponent of 1 there. Now we can finish it. Okay, so what would our equation now look like? The bases are the same. So the exponents must be the same. So 2x equals 1. We'll divide by our 2. And our answer for that one is x now equals 1/2. Does that one make sense now? Because if there's no number, we know it's just like a square root. If there's no number, it's a square root. If there's a number for the index on the root, it's a different root. If there's no power, we put the 1 there. Okay, got a couple more to look at here. Next, we'll look at question number 8. Wait, we just did 8, so we just did that one. 9's the next one. And 9 is exponential decay. Goes 243 e to the minus 0.014 t. Okay, t is a number of years. And let's read question 9. So the decay of 243 milligrams of an isomatote is given by this. T is a number of years since the initial amount, that 243, was present. Find the amount to the nearest milligram left after 72 years. So what are we going to plug in? We want to find 72 years later, so we're going to use t equals that 72. So we'll put that 72 in there, just like that. And we'll break it up first, so multiply up in there, in your exponent. And we've got 72 times a minus 0.014. And that makes it then a minus 1.008, 243e to that power. Let me double check and make sure I multiplied correctly. And I did. Okay, now, how do we do this again in our calculator? Well, the way we do it in our calculator, and I'll show you both styles of calculators, depending upon which type you have. Now, either one, what are we going to use? We're going to be looking for this ln key. So if you have this style of calculator, you would type 1.008, you would make it negative, inverse, ln, and then multiply that by 243. And that is then going to give you this. Now, what do they want? They want it to the nearest milligram. Okay. Now, how many is milligram going to be? Well, milligram is going to be 2 places, right? Because you've got tenths of a gram, and then we've got milligram after that. So, what would that be if I rounded? It looks like it's going to be 88.68. And that's going to be in milligrams. Oh, wait, it's already in milligrams, so we want it to the nearest one, so it's going to actually be 89 milligrams. Sorry about that. It's already in milligrams, so we don't have to round, right? So we'll just write that as 89 milligrams because that 243 is already in milligrams. So we just round it to the nearest milligram, and so there should be 89 milligrams left. Okay, now what about the other style of calculator? If you have this style, how would this style work? Very similar manner, a little bit different though. On this one, we do the second ln first. Let me find the ln key. Okay, and that puts that e up on the screen. Type in your number. Now, make sure you use the negative down here, the one with parentheses around it. Don't use this one. That's a subtraction. use the change sign button. Okay, so use that to change the sign. And now we want 1.008. It's going to be negative. We hit enter, and then we multiply that by 243. That gives me that 89 milligrams when you round. So you'll either have one style of calculator or the other. But either way, you should end up with 89 milligrams. And the last one that we asked about was question 14. So question 14. Very, very similar. Exponentials are used for population, modeling, and radioactive decay. Some other things, but mostly it's population and radioactive decay. So an element decays at a rate of that, where S is the initial amount in grams and T is the time in years since the initial amount was present. If you have 13 grams of this element, how many grams will you have 3 years from now? And you want to round to the nearest tenth of a gram. So when we look at this, we need to figure out what our S is and what our T is. Because we have a capital S and we have a little s. We need to figure out what the S is. Now, S is going to be the initial amount. So in our case, what's our sample size? Okay, the sample size, the initial amount present, is 13 grams. So that's going to go there. So S is going to be 13. How many years are we going to look at this? 3 years later. So my T would be what? T would be 3. Just plug our values in. So we want to find S of 3, and that's going to be 13e to the minus 0.050 times the 3 years. And that gives me then S of 3 to be, let me work it out, 13e to the minus, we'll multiply those together, 3 times 0.05, and it again is going to be a minus 0.15. We got that. Now, what's my final answer going to be? Let's do it in both calculators so we see. We take the 0.15, we make it negative. We want to use the second or inverse, ln. And then we multiply that now by what? Multiply that by our 13, and that comes out to be 11.1. Or 11.2 if you round. And what do we want? We want this the nearest tenth of a gram. So that's going to be, it looks like 11.2. And that's going to be in terms of grams. How would you use the other style of calculator? Okay, a lot of you have this style. A little bit different. Second, ln, it goes first. That puts the E up on the screen. Now, again, we don't use this key. What do we use? We use the one with the negative down here. Okay, so that's going to make that a minus. And then we have 0.15. We hit enter. And then we multiply that by what? 13. And it's going to give you the exact same answer. By the way, why is this exponent here negative? Well, it's negative because what's happening to the radioactivity of this isotope? Think about Chernobyl and some of those other radioactive places. What happens? Over time, they become less radioactive, right? It's negative because the amount of radioactivity is decreasing because this radioactive isotope is decaying. So that's why it's going down. Now, if you were looking at population, if it was population, this would be a plus because it's going up all the time. And so it would be going up this way. This one's going down because it's slowly decaying downward. So that's why this exponent is negative because it's decreasing all the time. If it was positive, it would be going up because the population is increasing. if you were looking at populations. Okay, does that take care of all the questions now? Okay, we'll go ahead now and look at 4.3. And 4.3 is logarithms. And logarithms is going to be brand new for a lot of you. So again, in the back cover of our textbook, we have logarithmic graphs. Logarithms and exponentials are the opposite of each other. They're inverses of each other. Because if I were to draw my exponential here, see, it would flip around and it would give you the logarithm. Now, when we talk about logarithms and we go to graph these, we have to look at our variable a, which is the base. It's just like this over here, that a was your base in an exponential. Now, when we talk about a logarithm, they have a base a. Base e is the natural log, ln. Let me kind of talk you through logarithms and how they operate. What we're going to be doing is we're going to be turning these logarithms into exponentials, and we're going to be solving them. This is an example of a logarithm. F of x equals log base, let's say, 5 of x. And we're going to try to graph this. Now, when I look at this, that a is your base. So that is the base. So when we talk about logarithms, the subscript, the number below, that is going to be your base. Now, just like with exponentials, we've got two different graphs. And the graph is going to change based upon the base. So, if your base is bigger than 1, it looks like this. If your base is between 0 and 1, it looks like that. So fractional bases will look like that. And notice we still have, instead of it being 0, 1 up here for the exponentials, right? We have 1, 0 here. So that changed it a little bit. Now we still have a comma 1. So that would be your base there. So whatever your base is, that becomes that value of x, not y, because they're inverses of each other. So when we look at this, the 5. 5 is greater than 1. That's our base. Okay. What does the graph look like? So a quick sketch of that graph. 5 is greater than 1. It's going to look similar to this. Now, when we graph these exponentials, we had a horizontal dotted line, right? Horizontal asymptote. These have a vertical one instead. So these have, it's not in your book, but there, when you go to graph these, there's going to be a vertical dotted line. On these, we also have the point 1, 0 for a new point, and we've got a comma 1. So they're a little bit different. Now, when I go to graph this, we know the picture's going to look like that. Are we shifting this graph up or down any? No. Is it being moved left or right? No. So that means my vertical line is going to be what? Right here at x equals 0. Now we fill in our points. So the first point is going to be 1, 0, and that's right here. Normally it would be 0, 1 up here, but remember, logarithms and exponentials are inverses. They're opposites. So instead of it being 0, 1, now it's 1, 0. So that's there. What's my next point going to be? A comma 1. So in our case, a is 5. So that's going to be 5. And up 1. So it's going to be right there at 5, 1. Now, you can do more points if you need to, but what's the graph going to look like? Okay. The graph is going to look similar to that. Okay. Let's do a couple more of these, just to make sure we understand how to graph these logarithms. Okay, if I want you to graph this logarithm here, well, that is my a, isn't it? Is 4 bigger than 1? Yes. 4 is clearly bigger than 1. So, what's my graph going to look like? That, isn't it? Okay, I always like to write a quick sketch over to the side, just so I understand that it looks like that. What about the minus 3? It's inside the operation and it's negative. So that moves it left to right. And in this case, it's a negative, so that's going to force this forward what? Forward 3 units. So when I go to graph it, I'm going to move forward 3. And that is going to be my new vertical line. So my new vertical line is x equals 3. So we have to move it over, right? Slid it forward. Okay, now, what do? Well, we need a new point, right? And it's usually at 1, 0. Now it's going to be at 4, 0, because you moved it over 1. You always move it 1 out. And then what's my next point going to be? Well, what's my base? 4. Okay, that's your A. And so that's going to now be 4 units forward from here. So 1, 2, 3, 4. And up 1. That's going to make my new point here. And if we count units, that would be 1, 2, 3, 4, 5, 6, 7. So that would be at 7, 1. And when I connect them together, we make the curve like that. So when I go to grade this, what am I looking for? I'm looking for the graph to basically look in this shape, and it's been slid what? Slid forward 3 units. Now, these have all been greater than 1 for the base. If it's less than 1, the graph is going to look different. So if it has a fractional base, then the graph is going to go the opposite way. It's going to flip around here. So if f of x equals log base, let's say 1/3 times x plus 5, what would that graph look like? Well, my base here is 1/3. So that's my A. Now, what do we know about A? Okay, A is between 0 and 1. It's a fraction. So my picture is going to look like this. It's going to be going down. Why? Because your base is A of 1/3, and 1/3 is between 0 and 1. So your picture will look like that. So your basic picture is going to look like this. Instead of going up, it's going to go down, and we still have the same vertical line. Now, what about that 5 inside? Okay, and why does it look like this? Because 1/3 is less than 1. Okay, it's between 0 and 1. 1/3 is less than 1, so that means it looks like this. That 5 is positive, so that's going to force it back 5 units. So the first thing I'm going to do is I'm going to go ahead and draw my vertical line at 5, at -5. So 1, 2, 3, 4, 5 units back. There is that. Now, what do we always have? We always go 1 unit in front for these logarithms. So we still have that point, and this is at x equals minus 5. So this new point would be at minus 4, 0. So there's one of them. Now we need the other part. Okay. Well, the other part, what's my base? 1/3. So that's going to be, if we look at it from here, minus 5, we're going to go back about 1/3. And up still 1, so my new point would be right here at about minus 4 2/3, comma 1, right? Because we use that base of 1/3, so it's 1/3 back. Now when we curve it, it's going to look correct. And when we curve it, see, it looks like it should. Where do I get the negative 4, 0? Okay, on here, on this one, this is at 1, 0, isn't it? It's 1 unit from that x equals 0. So when I slid this back to 5, negative 5 here, I slid it 1 more unit forward past the vertical, and that's why I've got the minus 4, 0 there, because it slides it forward 1. And now, instead of it going like the other one would have been, if this was 3, you would go over 3 and up 1, and it would curve that way, right? But ours is 1/3. And so if we're at 5, negative 5, we take away 1/3, that gives you basically minus 4 2/3 there. So that's why it curves and looks like that. Now, when we go to work with logarithms, in most cases, how we solve a logarithm is we can transform it into an exponential. So I'm going to show you the textbook formula and the page number so you have it of how to transform a logarithm into an exponential. Because remember, they're inverses of each other. And this is in 4.3. And let me give you the exact page number and the formula so that you have it. Here it is. Page 463. And we're going to practice working through a couple of these. We're going to learn how to transform them from a logarithm to an exponential, and from an exponential back to a logarithm. So we're going to do several of these where we transform them. So I'm going to write up our formula. And here's our formula. Y equals log base A of x. All right, so that can transform into x equals AY. So they can transform back and forth between each other. So here's an example of one that we can transform, and you can see how it works. And let me come up with a number here. 4 cubed, and 4 cubed is a 64. So we are going to transform this into an exponential. So we're going to transform this into an exponential. What do we know about the pieces? When I go to transform it, that's going to be my y. This is the a, and that is the x. So when I transform it, what does it now look like? X is going to be that 64. So that is here. Then we have equals. What is my base? My base is 4. What about the y? What is the y? 3. Now, does that make sense? Yes, because 4 to the third power is what? 64. See how I was able to convert it, right? It makes sense. You can convert logarithms to exponentials or exponentials to logarithms. Let's transform another one. Okay, so if I wanted to transform this one, label the pieces. This is your y, this is your a, and that's your x. So when I transform it, what does it look like? Okay, my x is that 25. That equals base of 5 squared. And that makes sense because 5 squared is what? 25. You see how we're converting them? You label them and you rewrite them. Now let's go the opposite way. Let's try to work with this one. How would I convert this to a logarithm? What would this be as a logarithm? We know 2 cubed is 8, so we know we've got it correct. What about the pieces? Okay, if we need to, we can rewrite up our formulas. I'll rewrite them again so we have them. And we use double arrows because it can go either way. You can transform right back and forth between the two. Equals a to the y power. So what is that 8? In this case, the 8 is out in front, so that's your x. 2 is the a, and 3 is the y. So what would this look like as a logarithm now? As a logarithm, it would be 3 equals log base 2 of 8. Is it kind of making sense how to transform them back and forth? You just write up your formula, label your pieces, plug it from one formula to the other. And sometimes it's easier to use a logarithm than an exponential. Other times an exponential might be easier to work with. Now we're going to work with some logarithms. And we're going to be learning how to use these properties, because we have some properties of logarithms. And we'll go through the properties, and we'll see how to solve some questions using these properties. So logarithms have unique properties. Logarithms are a little bit different. Now, logarithms are used for things where a small change is a large change. And an example of a logarithm that's being used is pH. That's a logarithm scale. And also hurricanes and tornadoes and earthquakes. Those are on the logarithm scale. Because a small change is a big change. When you look at an earthquake, to go from a 4 to a 5 on the Richter scale, that is a huge jump. That's like 100 times more powerful. So it's a huge jump between the numbers. Same thing with pH. When you go from an 8 to a 10 on the pH scale, that is a big, big change. They have these unique properties. Log multiplication can be separated out into 2 different logs. With addition, log division becomes subtraction, and we can bring powers down. Log of 1 is 0, and log of a, when the base is the same as the number inside, it becomes 1. So these are the properties that we're going to be using to work through and simplify down some logarithm equations. So I'm going to pick a few of these from our textbook to look at. And we're going to be using our properties here to solve them and simplify them down. So let me make up some, or I'll work them out. Let's see. I'll just try to pick a couple of these for us to try to work through. And I'll just make one up similar to the 2 in your homework. And if there's no number, if it's just a log, it's assumed to be log base 10. A lot of times, though, when we break these up, if it's a different base, it'll have a different number. But if it's no number here, no base, it's log base 10. And if it's log base 10, I'm going to show you how to use your calculator here. I want to break this down and I want to figure out the number. Now, the property that we use more than any other property is this. When you have a power on these logarithms, that power, that exponent, can come down. So I can rewrite this now as 5 log base 10 of 0.003. Is everyone okay with how I did that? Bless you. Now, I brought that down. How do I use my calculator to simplify it from further down? Okay, we want to get the decimal answer. Just like there was an exponential key, an E key in your calculator, if you look at your calculator, there's a log key. So we're going to be using that. Whenever you have base 10, you use the log key in your calculator. Now, next week, we're going to learn about change of base, where we can convert anything, any logarithm, into a common base 10. But if it's a log base 10, I can use my calculator. So how would I break this down? The first thing I would do is log base 10. On this style of calculator, I would hit my log key, and then I would type in 0.003. Then I would hit enter, and then I would multiply it by 5. And that gives me now, for my final answer, a minus 12 point, if we round here, 6, we'll just take it out 3 places, 614. So we use our property to bring that down. Now you could have just done this and then took the log of that, but you'd have to write it down. I think it's easier if you just bring the exponent out front. That's one of the unique properties of logarithms, is you can bring an exponent down. How would I use this style of calculator? This one's a little bit different too. If you have an inverse key, you're going to have to do it the opposite way. So you type in 0.003, hit your LOG key here, hit times 5 here, and that gives you the same, minus 12.614. So depending upon the style of calculator, you'll either hit the log key first or the log key at the end. One or the other. Let's do one more just to make sure that we know how to use our calculator for logarithms. So how would I simplify this one down? Well, the first thing that I would do is I would look at this, and I've got the 5 here. So I would go ahead and bring that down. So I would bring that down, and that's going to give you 5 log base 10 of 8. And you could even break that 8 up into 2 cubed and then bring the 3 down as well with the 15 in front. But we've got calculators. I don't think we need to really use the properties as much as we would have a long time ago. Calculators make things a lot easier. So if I wanted to work this one out, what would I do? If I use this style of calculator, all right, I hit my 8 LOG times the 5, and that gives you now 4.51 if we round 5. How would you use the other style of calculator? Okay, this style, you're going to have to type the log key first. So you type in log, and then log base 10 of 8. And then we hit multiply by the 5 there. And so that gives you the same 4.515. So the log key is built into your calculator. If we didn't have calculators, we'd have to use a table. 50 years ago, we would have to use a book of tables. We would have to find the logarithm. It's a much more complicated process to use tables. Calculators have made our life so much easier. We don't have to get out logarithm tables anymore or use slide rules. That was another way of doing things. So we're really lucky that we have calculators. Now we're going to look at some where we have to find a logarithm when it's raised to a power. So let's look at this one. How would I break this one down? Okay, well, what do we do first? The first thing we always do is work with our exponentials. Our exponents go first. No parentheses. So I'm going to do this piece right here first. And you can either keep it stored in your calculator or you can write it down. Either way. So first thing I'm going to do is I'm going to do the log base 10 of 4. So I'm going to do the log of 4. And that gives me that. Okay. Now I'm going to show you how to use the answer key that's built into your calculator. So that's what we've got right here. Now, if you go down and you look on many modern calculators, you're going to see the A and S in a different color. That is the memory that's been stored. So that number right now is stored in memory. I could write it all down, but it's stored in memory. So what I can do is I still need to take the 5 to that power. So I can hit 5, caret, and then I can go down and I can hit the second key, and the A and S, that's your answer. And I don't have to write the number down, and that gives me my final answer, which is 2.635, if you round, close enough. 3 places is usually enough. How would you use the other style of calculator? This one's a little bit different too. Every calculator is a little bit different, but somewhere you're going to have a memory storage. So on this calculator, you would type 4 log. That gives you that. Now, you can either write it down, which is an option, or you can use the store key in your calculator. For this style of calculator, you hit the store, STO, okay, that's going to store it. And you can clear this out. You can hit 5, and then you have to hit your YX key. And recall here, and that's going to recall that answer back out, and that's going to give you the same 2.635. Or, what's another way of doing this? If you don't want to use the memory buttons in your calculator, you can do this. We know that, let me write it right here. Log of 4, if I do that, is this. So I could just write this down. If I wanted to just write it down, I can do that. Right? I could just write it down because that's what it is. And then clear that out. I can take 5 and then your caret or your YX key. And then 0.60206. And that gives you the exact same answer. So either way, you can either write it down or you can use the automatic memory buttons in your calculator. If you take statistics, you're going to use the automatic memory buttons in your calculator a lot more. Because statistics is all calculator work. So if you take elementary statistics, you'll be using a lot more of your calculator. In this course, we don't really use it that much, but your calculator can store everything in it. All those answers can get stored. Now we're going to work with some of these where we have to find the base. So I'm going to give you a function, and you're going to have to find the base and then evaluate it down. So I'm going to give you a function here, and you're going to have to find the correct base using one part of it, and then use that then to get the other part. thought there was some in the textbook. I'll just make up some because the textbook doesn't have any for us to work through. But they are in your homework. So I'll make up one just like your homework. Let's see here. How about F2? Yeah, let's make that an 8. Equals 3. Let's plug that in. Okay, now I want you to find the base. So if I was to plug this in, I need to figure out the base. So if I give you this, I want you to find the base. So find the value of A. Now, if I rewrite this, we've got f of 8, okay, and if I plug my values in, that's going to be log base A, unknown, of 8, right? And we know that f of 8 is what? What's it given to be? 3. Now, what is my A going to be? How would I find the A? Well, you have different ways of finding it. One way is to just look at this. What number raised to the third power is going to give you the 8? Can you tell me what the base would be here? 2. So in this case, my A equals 2. Another way to look at this is just to convert it, and you'll get the same equation. Now we know A is going to be 2, and we could do that just by looking at it. How would we convert this from a logarithm to an exponential? If I wanted to convert this from a logarithm to an exponential, we use this. Y equals log base A of x converts into x equals AY. And so if we have 3 equals log base A of 8, that would convert into, we did this earlier, this is your Y, that's your A, and that's your X. That would convert into now what? 8 equals A to the third power. And you found it a minute ago, right? Because what's A got to be? A must equal 2, right? Because 2 to the third power makes it what? 8. Now, once I have that, then I'm going to have you find a value. So now we know if A is 2, then my equation becomes f of x equals log base 2 of x. And I want you to find, let's have you find something here. How about I have you find f of, let's say, f of 9. So move this up so we can see it here. So we found our A. I rewrote it. Now, I want you to use this equation here to find f of 9. Well, if I wanted to find f of 9, what is that now? F of 9 would be log base 2 of 9. What would that convert into? Because we don't know this part here. This is your Y. So we basically have this. What would this convert into as an exponential? Because f of x is the same thing as y. So we plugged in that number 9. If I wanted to convert this to an exponential, what would it look like? Okay, let's look at our formula. Y equals log base A of x. That converts into x equals A of y, right? Okay, so what is that going to look like when I go to convert it? if I want to convert that, let's just make that, let's make sure it's going to work. Okay, I just want to make sure it'll work here. Sorry about that. Let's make this, just to make it easier, let's make this a 16, not a 9. Sorry about that. This way it converts correctly. If I use a 9, it won't work right. So use the 16 then. Sorry about that. Let me make sure that's a 16. This way it'll convert correctly, because 9 won't, because it has to be a power. Okay, so of 2. So when I convert this, what would this convert into? If I convert it using our log formula, y is your y, this is your a, and that's your x. So when I convert it, what does it look like? It looks like 16 equals 2 to the y power, and what would y be? What would y be here? Anybody know? Okay. 2 raised to what power gives you the 16? Use your calculator. 2 squared is what? 4. 2 to the third is what? 8. 2 to the fourth is what? Yep, 2 to the fourth is going to be that 16. So we now know that y has to be 16. So we now know that for our final answer, I want you to find f of 16, f of 6, oh wait, 4, not 16 here. My mistake. Yep, sorry about that. My mistake, should be a 4, not a 16. So we now know that f of 16 equals what? 4. I'll do another one so it's not so confusing. It's just a lot of transforming. We have to find the base first, and then once you found the base, then I'm going to have you find something else. So let's do another one where we first have to find the base and then use that base then to calculate a new exponential value. So let's say we have, and I'm trying to use the same directions here. Suppose again f of x equals log base a of x. And I'll just do the one from your homework. I'll just do question 10. And f of 5 equals 2. I want you to find f of 125. So this is what I want you to do. And this is actually your homework. Question number 10. So 4.3, question 10. So I'll go ahead and work this one out. And I will leave 9 for you to do. These are the only 2 really kind of tricky ones. So this is question 10, right? Okay, so if you want to write it down and have it, you can. What am I going to first do? Okay, the first thing I look at is I look at f of 5. So f of 5 would be now, when I plug it in, log base a of 5. Now, what do I know about f of 5? What is f of 5? F of 5 is defined to be what? 2. So we know that. Now, how do I find my a? Well, I've got to convert it. So let's convert this to an exponential. So what would this convert into? If I rewrite this, remember, this is your y, this is your a, and that is your x. So when I convert it, I now have 5 equals a, which is unknown, squared. Is everyone okay with how I did that? Now, we have done many, many of these before. This is a common exponent. It's a square. How do I get rid of a square? What operation am I going to use to get rid of a square? I'm going to use a square what? Square root. Okay. Now, with logarithms, you can't have a negative base. So, when you take that square root, you don't have to worry about the plus or minus. I'm working this one out because this one gives you a square root base. The other one, 9, gives you a whole number base. So I converted it. I found out my equation, and now we know that a equals the square root of 5. Now we can rewrite it, and now we can finish it. So let's now rewrite this, because our base is the square root of 5. So now when I rewrite this, we've got f of x equals log base a, but a is the square root of 5, x. Okay, that's our new equation. We just rewrote it. And now I want you to find, so this is the second part, now I want you to find f of 125. So f of 125, when I plug my value in, is going to be log of the square root of 5 for the base of 125. How do I convert this and work with this? Well, this is your y. So I can rewrite this as y equals log base the square root of 5 to the 1 of 125. Rewrite this again. Remember, this is your y, this is your a, and that is your x. And how do we convert them? In case you forgot, let's write up our conversion formula. Y equals log base a of x converts into x equals ay. Right? So when I convert this, what would this convert into? 125 equals a, which is the square root of 5, right, to the unknown power y. How would we find our y now? Right, we've got everything we need. We should be able to find that y. Well, different ways of approaching this one. We need to somehow get the bases and the bases to be the same so that the exponents are the same. And again, there's different ways of approaching this. You're going to get the same result either way. I'm probably going to get rid of the squares. So I'm going to probably square both sides, and that'll get rid of my square root. Because remember, what happens when you square a square root? It goes away. So now we've got 125 squared equals 5y. And what do we know about 125? 125 to the second power, 125 squared. We just work it out, and that gives you this. Now we should know what to do. We need to make sure that our bases are the same. So, 5 raised to what power gives you that 15,625. That's going to be our y there. So what are we going to do? We take 5 squared. Okay, 5 squared. 25 doesn't work. 5 cubed is what? 125. 5 to the 4th, we're getting closer. 625. 5 to the 5th power is what? 3125. And finally, 5 to the 6th power is going to be what? 15,625. So that means then that this can be converted into 5 to the 6th power. And now are the bases the same? Yes. So that means y equals 6. So that tells me then that f of 125 is what? 6. This was the most difficult one, and that is why I chose to work it out for you, because it has a square root base. The other one, question 9, is much, much easier. Now, you will be plugging in a fraction, but you can deal with that fraction a lot easier than you can something where you have a square root base, like this one. That should now finish up 4-3. So I'll go ahead and let you out a few minutes early, but I'm going to pass out the sign-in sheet, and then I've got homework to pass back as well. Okay. Here's the sign-in sheet. Make sure you sign the sign-in sheet. And a lot of you have homework that you haven't